In terms of real solutions to a quadratic equation, there can be 2, 1, or 0 such solutions. In this video, we look at examples of quadratics that have complex solutions. Let's start with an example. Can the area of this square be modeled by this quadratic function, y equals x squared plus 1? Describe the roots of this function. This is the graph of the function. Notice that it doesn't intersect the x-axis, so this function has no real roots. This means the function can't be written as the square of a binomial, which is what would be needed to model the area of a square. A function that doesn't intersect the x-axis doesn't have real roots, but it does have complex roots. Let's take a look. We start with the function y equals x squared plus 1 and set it equal to 0 as shown here. Subtract 1 from both sides to get x squared equals negative 1. Take the square root of both sides to get x equals the square root of negative 1. The square root of negative 1 is not a real number. It is an imaginary number. It is part of a different number system called complex numbers. Complex numbers can be written in the form a plus bi. The term a is known as the real part because that term is a real number. The bi term is called the imaginary part because the expression is a multiple of the imaginary number I. Let's look at another example. What are the complex roots of this function? Y equals x squared plus 4x plus 5. Graph the roots on the complex coordinate system. For this quadratic, we can use the technique of completing the square to find the roots, even if they are complex roots. Recall that with completing the square, we want to end up with the square of a binomial, as shown here. In the expanded form of the square of the binomial, notice what happens to the a term. Note the 2 times a term here and the a squared term here. So let's start with the basic quadratic. Notice the 4x term. We can rewrite it as 2 times 2x here. To make the expression in parentheses a perfect square, we need a 2 squared term here. In order not to change the value of the left side of the equation, we also need to subtract a 2 squared term. We get the binomial squared term here, and we simplify the numerical terms. We subtract 1 from both sides. Then we take the square root of both sides. Notice that the right becomes the square root of negative 1, defined as an imaginary number. Isolate x to get the 2 complex roots. The graph of these roots is shown here. Notice that the horizontal axis is for graphing the real part of the expression, and the vertical axis is for the imaginary part. The 2 complex roots are shown. Let's look at a final example. This function has no real roots. Y equals x squared plus 2x plus 3. Compare the roots of this quadratic as the constant term goes from 3 to 2 to 1. You can see from the graph of the function that since it doesn't intersect the x-axis, it has no real roots. Let's start by finding the roots of the given quadratic. For this, we use the quadratic formula. The b value of 2 goes here and here. The a value of 1 goes here and here. The c value of 3 goes here. Simplify the expression in the numerator. Notice the square root of -8 becomes 2 times the square root of 2 times the imaginary number I. The complex roots of the equation are -1 plus the square root of 2i and -1 minus the square root of 2i. Now let's look at the root of the quadratic with 2 as the c term. The b value of 2 goes here and here. The a value of 1 goes here and here. The c value of 2 goes here. Simplify the expression in the numerator. Notice the square root of -4, which becomes 2i. The complex roots of the quadratic are -1 plus or minus I. Now let's look at the root of the quadratic with 1 as the c term. The b value of 2 goes here and here. The a value of 1 goes here and here. The c value of 1 goes here. Simplify the expression in the numerator. Notice that there isn't a square root of a negative number, so there aren't complex roots for this quadratic. In fact, there is only one root, -1. This means this quadratic is a perfect square. A graph of the three sets of roots on the complex coordinate plane reveals an interesting pattern. The green point is for the real root of -1. The red line segments indicate the complex roots for the c value of 2. The black line segments are for the complex roots for the c value of 3. But notice all three sets of roots, whether real or complex, are on the same vertical line that cuts through x equals -1. Also notice that these roots are symmetric about the x-axis. In other words, the complex roots are mirror images of each other along the x-axis. Do you think this behavior is consistent across whole families of quadratics whose only difference is the c value?